I know naming reactions is a bad idea, but let's go ahead and do it anyway. This first step, you're doing an aldol and a condensation. And that next step, you're running two reactions. The first one is a Gilman addition. Actually, sorry, let's switch that around. Ooh, give me a second here. My screen looks... we'll do a Michael addition, followed by... Is it named? Let me think what the name was. Yeah, it may just be alkylation. Okay. Yeah, it's an alkyl halide, but I don't know what I would name it. We can really do this then in 1, 2, 3 steps. Okay. So approaches to this, I'm trying to figure it out. Number one, we do have that intermediate floating through the middle, so that does make this a little bit easier to process. I notice most people try to go through and process that step 2 and 3 first, getting to your final product, then looking at that first step. So if we focus there, what we can see is that we have an electrophile at that position and a nucleophile there. It's going to end up being our balance. Okay. You may not see the nucleophile right away, so we could erase that temporarily. So we've got that electrophile chemistry first, so we have to address it first, and we can do that by adding that carbon piece as our electrophile, so as our nucleophile. So where do we get a carbon nucleophile from? Okay. A lot of different places we can get negative carbons. Okay. So we need a negative CH2CH3. The problem is that if we have a negative carbon, more commonly, that does what type of addition? The carbonyl carbon, or our 1,2 addition, right? Or our kinetic product. We don't want that. We want the 1,4 addition. So how can I get a negative carbon that gives me 1,4 addition? That is the Gilman reagent. That's where I need to see the copper compound come in. Okay. As far as knowing the exact formula for that, I wouldn't stress on it. Okay. If you nail down that you've got an ethyl group and you know you have copper in it, you've solved your multiple choices question out the gate. Okay, so that's what I would focus more on. When we run the Michael addition, very commonly is done in 2 stages. We do the first part with our nucleophilic addition. When that nucleophile comes in and attacks, the electrons in that bond end up sitting on that carbon. So we almost always follow it with a second step. That second step neutralizes that negative carbon by adding hydrogen. Okay. Every time you do the Gilman or your Michael additions, you almost always see a second step where you're adding a hydrogen. Much the same as every time you do a Grignard reaction, we follow it with adding a hydrogen. Okay. For your standard Michael additions, you almost always follow it up with ammonium chloride, but it can be any hydrogen source. Under this circumstance, do we really want to put a hydrogen right on there? No, because in the very next step, I'm trying to do an alkylation, where I can then attach something to that position. Okay. Well, I now have a carbon nucleophile, and if I look at that new bond, I'm connecting 2 carbons. So I'm going to need a carbon nucleophile to get this reaction to work. So let's not kill the carbon nucleophile right away. Let's leave it there and move immediately into our second step. And instead of it being a hydrogen that I can add, I can then go through and do the alkylation where I add all of those carbons. 1, 2, 3, 4. Okay. That carbon needs to be positive. I'd have a primary carbocation, not allowed to throw in, number one, a primary carbocation. But when we're looking at our syntheses, we can't throw in a charged structure. We have to start with a neutral structure. So how can I get a positively charged carbon? I need something more electronegative than carbon to withdraw the electron density away. right? Lots of things are more electronegative than carbon, but we also want to limit any other side reactions. So what we'll do is pick a functional group that we can add to that that has no other chemistry. Pretty much any halogen would work perfectly well. Okay? So that gets us through the tail end of our experiment. The beginning part of the experiment is trickier to evaluate, but what you should be doing is identifying what piece is missing. If I go through and look at the starting material carbon structure and highlight that same starting material carbon structure, it's right there. Okay? It cannot be the other piece. Why can it not be the other piece? I'm missing carbons. Okay, so that makes that a little bit trickier. So if those are my pieces, I'm now looking at reacting somehow those two carbons. If I look back to my starting material, what chemistry is available to that red carbon? I have alpha hydrogens, which are acidic. If I remove one of those hydrogens, what charge does that carbon become? Negative, and I now have a nucleophile that can go through and react in an aldol condensation. I now need to supply the other piece. I think I did count that, right? Okay. And we would need an aldehyde. So there we go. How do we remove that hydrogen? What did we say we needed to add? We needed to add a base to remove that hydrogen. What are some strong bases? Sodium hydride, LDA, lithium diisopropylamine, and do OET, any of our ethoxides. Okay, we could even use T-butoxide. What's the difference between T-butoxide and OET, our ethoxide ion? T-butoxide is sterically much larger. Okay? So all of these bases have the opportunity to pull off the hydrogen. Do they all have an equal opportunity to pull off that hydrogen? No. Why? Out that other position, I have another alpha hydrogen, which means the base I choose had better selectively remove the red hydrogen and not the blue hydrogen. I need to form the least substituted enolate, which would be the kinetic product, not the thermodynamic. When we look at our base choices, only sodium hydride and LDA will get you your kinetic product. The T-butoxide, even though it's bulky, will still produce the, I guess I should box that in red, will still produce your thermodynamic product, which is going to give you your wrong answer for this. T-butoxide will end up removing that blue hydrogen. So we have to be very careful in our choice of base. Questions? What's that? Ethoxide is going to be even worse than T-butoxide because it is sterically smaller, which means it can get into the blue hydrogen even easier than the T-butoxide can. So ethoxide is going to get you the same issue. You're going to end up forming the thermodynamic enolate, not the kinetic, and you need the kinetic to get this to work. Okay? For those of you panicking about quiz scores, as long as you identify that we needed a strong base, I'm happy with that, and we'll give you points. Okay, what we're doing is pointing out the weaknesses of those potential syntheses. Okay? So, I take my ketone, starting material, I take my aldehyde, put them in the same pot, and I add LDA. Is that going to work? What we're saying is we take, let's clean that up. We take these three things and we put them into one pot, and we say, there we go, now I'm going to get this product. Gina, you're shaking your head no. Why no? I think you were shaking your head no.
Yeah. You would have LDA attack first or grab the hydrogen first.
So in this circumstance, there is no first. So why do you want a first in there? What were you going to state?
So get a lot more than just that product.
This is going to give you a lot more than just the desired product. LDA will react with any alpha hydrogen. Our aldehyde also has an alpha hydrogen. That could form a nucleophile. It's going to give us side reactions. So when we mix our reagents, we have to make sure we mix them in such a way that we get one product. Okay. One way to do that would be to combine these two as a step 1, followed by a step 2 of the aldehyde. That will get me to that expected product in a very high yield. I don't have to worry about self-aldols at that point because LDA is such a strong base that it completely converts that starting ketone over to the enolate, and I don't have to worry about any self-aldols. There's no nucleophile if it's in the enolate state. Yes?
But isn't there only, in the second aldehyde, isn't it the same problem as the first one? There's only one hydrogen, so the LDA would attack.
But in the aldehyde, is the aldehyde acting as the nucleophile? Aldehyde is acting as the electrophile under these circumstances. I don't have to worry about it, and since I put it in as a second step, okay, theoretically by the time I add it in, everything's been converted to the enolate from the ketone. Now I have a nucleophile, one electrophile, one reaction, one product. One pot, I get tons of products. Because yes, that aldehyde has that potential for that alpha hydrogen. Other questions?
So just make sure it's not one pot and then
Yeah, you're going to have to be careful with those individual steps. Yep.
Don't you also need like a third step for the acid hookup to protonate one the oxygen before you do the aldol addition?
The aldol addition doesn't, I see what you're saying. You don't need a workup in that case. Your solvent would supply enough hydrogens. You'll notice that we haven't specified a solvent in this case. The solvent would be an alcohol. Because you need to get those two things to mix. Believe it or not, I think this reaction is going to run even without that proton source because it'll sacrifice a proton from somewhere else in our structures. I think that's what you were asking about. Okay. Other questions? Yeah?
Is the sodium hydroxide going to act like an LDA with a tap?
Sodium hydroxide, at any time, so our bases are hydride, technically amide are LDA, and an oxide, any oxide. Hydroxide, ethoxide, butoxide, all of those are going to give you the thermodynamic enolate.
But I meant the sodium hydride, is it going to act like an LDA?
Sodium hydride will act like LDA.
Which it would attack on
The least substituted enolate will form. That may be counterintuitive because we look at sodium hydride and we say, well, how big is it? Okay. If you look at just sodium ion and hydride ion, that is incredibly small. We might say, oh, that's really, really small. We would expect the thermodynamic product to get in there easily. But it's so small, it's not soluble. If it's not soluble, we're looking at a heterogeneous reaction, solid phase, liquid phase. It's massive. Okay. Other questions? Okay. Based on the quick quizzes I saw, you all did a really good job piecing that together. You're starting to pick up the ideas on finding these syntheses. It's not easy. You guys are doing good at it. Okay. Keep it up. There were definitely a couple other slides back here I wanted to talk about first. So we ended on our Michael reactions. The enolate attacks a beta carbon. Okay. This has to do with the strength of that nucleophile. Your enolates are resonance stabilized, They tend to attack the beta position. The carbon is not a strong enough nucleophile to attack the carbonyl carbon. Okay. Depending on how you decide to study it or present the material, so this came from an old textbook that we were using. They went through and said, well, we don't need to talk about the chemistry. We just say that these are examples of Michael donors. These are examples of Michael acceptors. When you put them together, you're responsible for the answer. Right? What we've talked about is not just saying Michael acceptors, Michael donors, but looking at the functionalities within those structures. All of the Michael donors are acting as what type of nucleophile? Careful. What's the nucleophile in all of the Michael donors shown up there? Carbon. It's a carbon nucleophile. Okay. We've seen carbon nucleophiles before. Grignard reagents are carbon nucleophiles. Why the sudden change when we look at the Michael donors, our carbon nucleophiles under this case, do we see different chemistry appear? What do all of these Michael donors have in common that say a Grignard reagent, which I know is going to be tiny at the bottom of the screen, that a Grignard reagent does not have? Go for it, keep going. Resonance stabilization of the nucleophile, which means the nucleophile now is not as strong as in the case of the Grignard. We start to see a separation in the type of reactions we get, hence the Michael donors. Okay, why we refer to it as the Michael addition. Okay. Of those, all of them have the same characteristics, lots and lots of resonance, except for the Gilman reagent. The Gilman reagent doesn't really have any resonance. That's the one extra one that you're going to have to just kind of tag on as part of your memory. Okay. The rest are all resonance stabilized negative charged species. To get the carbon negative, what did we have to find at the alpha position to our negative charge? So now we're referencing our negative charge. The alpha position to all of my negative charges, what do I find? A polar pi bond. Okay? Because what is that polar pi bond doing? Providing a way to stabilize the nucleophile. Okay? If the nucleophile is now slightly weakened, I can then react it with a Michael acceptor. What do we find in common for all of our Michael acceptors? They are all alpha beta unsaturated carbonyl compounds, or polar pi bonds. Every single one of them. Polar pi bond and a carbonyl. What do we see at the alpha beta position? An alkene. There's another carbonyl. Alpha beta, alkene. What do we have between carbon and nitrogen? Polar pi bond. Go to the alpha position. What do we have between alpha and beta? Again, another alkene. So it's finding the common pattern and repeating that pattern. Find the chemistry, the reason why that chemistry is there, and then just negative to positive and just crank it all the way out. Okay? Based on the people that I've been seeing in tutoring centers or in the tutoring center, you guys have been doing a very good job and have started, we've eventually pushed you hard enough that you're now actually drawing every single step of these god-awful mechanisms. So if we look at the mechanism for this Michael donor and our Michael acceptor, we're looking at something that is 4 or 5 steps. And yes, it sucks to draw it all the way out, but you're doing it. Good job. I commend you for that. Okay. Do you guys want to take a moment to draw this one out, and then we can try and draw it out together? Yeah. Okay. To explain why this mechanism is valid, one of the things that we would probably address would be right here at the beginning that we have resonance stabilization of that compound, of that enolate. If I do not have resonance stabilization, what does that mean about the existence of that enolate? Say that again.
Probably doesn't exist.
It doesn't exist. If it doesn't exist, can I run the next step of the reaction? No. Okay. So every time you're doing these, you're removing a hydrogen. Which hydrogen are you removing? the most acidic one. Okay? So pull off a hydrogen. If you can't show that that hydrogen was acidic through resonance stabilization, then that was not your Michael donor. That was not your nucleophile. We've got resonance to show that that works. Okay. We also have whoa.
How many you want? So we are throwing things out.
Yeah. We also have resonance stabilization of that first intermediate. Okay. Which helps to explain why that reaction is allowed. Kind of makes sense? So you're trying to identify each of the pieces, and at each step you say, is this valid? If it's not valid, that's fine. You just made a mistake. Go backwards, try again. Okay? Do all of that not valid stuff in your homework. Okay? Stop trying to get the answer. Because on the test, what will happen is you won't know what the answer is, and you will end up trying to get the answer through all the wrong answers. It's a bad method. Okay? So right now, focus on trying to get the wrong answer. Say, okay, well, what happens if I break that bond? Draw the result. Did it work? No? Break a different bond. Still didn't work? Break a different bond. Break a different bond. Break a different bond. You'll get used to the pattern of recognizing how things aren't going to work as well. That will help you solve answers quicker when you get to the exam. Failure is a good thing. Just don't do it on my tests. Okay? Questions? I know that's selfish. Don't do it on the final either. That's not my test. One more concept that we'll bring up. We've already talked about enamines, but we can use enamines in conjugate addition reactions. Okay? So if we had the enamine, we started with, say, do I have another structure here? I don't have another structure. If we started with that cyclohexanone, we could convert it across to the enamine, and we'd have that as our intermediate. Well, if I was then going to use that as my nucleophile in a conjugate addition reaction, the enamine is actually a little bit better of a nucleophile than our standard enolate. Why? Why is that attack now sped up a little bit?
It's not as, it's not as electronegative, so.
The nitrogen being less electronegative can donate its electrons in, making that carbon a slightly better nucleophile. It speeds up the reaction. Kind of cool. Take it a step further. Okay, so we still get this 1,4 addition. What happens if I go through and I tried to run the reaction with an extra methyl group? This is a tricky question. If we go through and look at the enolates or let's do the enolates for the carbonyl compound. There are two of them. We've got that enolate, whoops, and we have that enolate, where our nucleophilic carbon is at different positions. We go through and look at the enamine. Both of those are possible options, but what we, end up finding, sorry, I drew that wrong. We only form the kinetic enolate with the enamine. We will never form the thermodynamic. So if we were going to try to use this carbonyl compound in, say, an aldol reaction, okay, or any one of those other reactions with carbonyls, generating that carbon nucleophile, okay, We'd have to be careful with the choice of base, because if we used ethoxide, we get the thermodynamic product, which means we end up with the thermodynamic enolate, thermodynamic nucleophile. If we used LDA, we move to the other product. Okay? So our oxide bases get us our thermodynamic product. Our nitride or hydride bases get us our kinetic product. Always, when we use the enamine, we get the kinetic product, and we only get the kinetic product. Why is the thermodynamic now not possible?
Has to be something with the difference in the activation energy of the intermediate.
Sort of, yes. It has to do with that transition state. Okay. For those of you in lab saying, why do I care about this? You care about this because this is the answer to one of your questions in the lab. And why is this even more important for us as far as our chemistry goes? Well, if you go into lab and I give you sodium hydride or sodium amide with and you spill it or touch it on your skin, what happens? You go to the hospital. That doesn't look good for me. Okay? But if that's the nucleophile I want, well, now I'm forced to use that. Enamine comes along. Now that's only the only nucleophile I get, and I can use a weaker base. I don't have to use LDA. I don't have to use hydride. I can use any base to get my kinetic product. This is good because we use milder conditions, better for safety, better for the environment. Okay? But it still comes down to this why. Okay? Let's draw out, make our subtle changes here. If I was to make that thermodynamic, this is our thermo enamine versus our kinetic enamine. What is the difference between those two? Oh, this even doubles back to another chemistry that we've seen before. What's that? Yeah, why is the substitution different? Why is the thermodynamic prevented, whereas the kinetic is okay?
The thermal has no hydrogens attached to that position.
True, but why is that relevant? What's the atom difference in this case? There's just a random correlation. What's our big atom difference? What's the atom we changed that all of a sudden now eliminated the thermodynamic product? No. It was nitrogen. Okay. Nitrogen, and all of a sudden we get a kinetic product, our least substituted, or nitrogen, and now we don't have the thermodynamic product, our most substituted. Have we seen nitrogen mess with this before? Matt? In the question that you just worked on?
Is it that it's
The Hoffman elimination? What happened in our Hoffman elimination? Which double bond was formed? The least substituted. Why did the least substituted double bond form in the Hoffman elimination? You had a massive leaving group. Okay, we don't have a leaving group in this case, but the nitrogen is starting to compete in this case. And you'll notice that one of the big changes here is not just that I have nitrogen, but what did I put attached to the nitrogen? R groups. Does oxygen have those R groups? No. What are those R groups somehow doing? This R group is now in the same plane as this R group, which means I have sterically put two electron sources right next to each other. That close proximity of the electron sources destabilizes the thermodynamic product. Yep, and I'm going to have to draw it on the board too, because Jimmy can't see what we just pointed at. If we look at the R groups on our thermodynamic product, due to the stereochemistry of our resonance, or sorry, not the stereochemistry, due to our resonance, the nitrogen, the R group, number 1, our nitrogen, the carbon, and that R group are all in the exact same plane. Which means those two R groups butt up against each other and we get steric repulsion. If they repel each other, what happens to the energy of the thermodynamic product? It skyrockets. And what we might have predicted to be thermodynamically more stable now becomes thermodynamically less stable. And our kinetic now wins out. Okay. Why do we not see that issue in our kinetic product? We still have those 4 atoms. Why are they not in the same plane?
There's more space.
As a hint, it has to do with that carbon. Say that again, Princess?
What starting material, the hydrogen would be anti to the...
We don't even have to look at that.
Oh, we have an SP3 carbon.
It's an sp3 carbon, which means the geometry at that position is now 109, not all in the same plane. In the previous case, our thermodynamic, those are all trigonal planar atoms. Your atoms are now all in the exact same plane. As soon as we make it tetrahedral, pop, it's now out of the plane. We have a more sterically favored position. Enamine chemistry really helps out when we go through and do these types of reactions. So it's more of a lab, hey, this is neat thing, than a lecture thing, because you probably won't ever see it pop up in the lecture. Okay? Questions on that?
So that's the 1, 2?
This still favors 1,4 all the way through. Okay. One of the other secondary features is that if we try to, say, alkylate a carbonyl compound, okay, it becomes more active, and it is actually likely to polyalkylate. Okay. If we go through and make it an enamine, we see less likelihood of a polyalkylation from an enamine than we do from the enol. Kind of subtle little random chemistries. Again, not that big of a deal, but it's kind of a neat observation. Enolates do the same thing as our enamines do the same thing as our enols. Why? What do we have? What is effectively a keto-enol tautomerization? Right, we have a carbon nucleophile. Once we have a carbon nucleophile, it's going to start doing the exact same chemistry that everything else has been doing. We have an acidic alpha hydrogen next to a polar pi bond. It's identical chemistry. I will kind of throw out there that you see new names pop up. This iminium stuff, don't stress on it. Okay? Officially, there's a billion different functional group names. You're not responsible for knowing all of those functional group names, so don't stress on how those are directly referenced. You guys want to try this one? Okay, I'm not going to give you long. 2 possible answers depending on how you see and break it. We've got one in red and one in blue, so I've highlighted the bond to make or break those. We're doing our enamine synthesis through a Michael addition, okay, or our alpha-beta unsaturated carbonyl. So all I did was split, break it apart, and we get our 2 possible starting materials. Okay. We've got the alpha-beta unsaturated ketone, so I'll call it alpha-beta K, or our alpha-beta K. The other one would be our enol, okay, or our enolate, our active nucleophile. This said to go through an enamine synthesis first, so that means really before I react those 2, this guy needs to be an enamine. Does it matter which one you pick? No, doesn't matter. I just happen to pick this one because that's one of your more common ones. To get that, how do you get it? Sorry, I ran out of space, had to slide the carbonyl over, and we reacted it with, I think it's pyrrolidine. Okay. That gets us our enamine, which gets us to almost our final product. We'd have the nitrogen still attached. How can I convert an enamine to a carbonyl? It rhymes with I don't know what to say. Rhymes with daughter. How about that? Water. Okay, quick. What rhymes with water? That's what I thought. Don't make fun of my choices. You can't give me something better. Okay, so we can tag at the front end and the back end. The front end gets our enamine synthesis. Our back end is the reverse. To do the reverse, all we got to do is supply an oxygen. Water's a good source. It's almost always catalyzed, say, via acid. Okay. We could theoretically do the same thing with the other side, with the blue option. Why do I say theoretically? What we're saying is that this needs to be our enamine. Sorry, close enough. To go backwards, I would then take it down to our carbonyl. We would do our enamine synthesis. Everything looks identical, right? I even do this, our H2O and our H+. Everything's the same. Why is this reaction wrong? Steric hindrance is coming into play here. When we look at our red reaction, where are our alpha hydrogens? Right? Those are our two alpha hydrogen positions. Are they different from each other? No, they're identical, so it doesn't matter. Look at the blue one. I have two different ones at my alpha position. What's further more important? Which alpha hydrogen gets removed from the enamine? The kinetic product, not the thermodynamic, which means the nucleophile is that carbon, which does not get us to our final product. Make sense? See the pieces? Unfortunately, I have to roll through this, so I'm going to have to go forward. If you got questions, talk to me after class. Robinson annulation. I'm not going to draw out the mechanism on this because I know a lot of people have gone through and done it already. It is just long and tedious. It's doing the same chemistry that we've been doing all the way through. You now just stack it. Okay? The very beginning of this is just your addition. So we start with a base. The base needs to remove the most acidic hydrogen. In this case, that red hydrogen. Why is that red hydrogen more acidic? Doubly resonance stabilized because of the carbonyls. That gets that carbon to now be a nucleophile, which can then attack here. You've now done your Michael addition. Once you've got the Michael addition, you would end up with this material, which has still a lot of base present. So we could now potentially do an aldol condensation. Lots of alpha hydrogens as potential reactivity. There's 1, 2, 3, 4, 5. Whoops. There's not a hydrogen in that middle one. There are 4 positions that could potentially react to do your aldol condensation, which means you get 4 possible products. I'm going to simplify that for you. You get 3 possible products. Why did I make it 3 instead of 4? what's the difference between these two positions? Nothing. They are enantiomers of each other. Okay? So we're really, if we ignore stereochemistry, we really only have 3 possible products. Those of you in lab are already answering this question that I'm going to ask. Draw all 3 products. Okay? I'm going to skip ahead at this point, but you should be able to go through and draw all 3 of those products and come up with an explanation for why we only see the product shown and not any of the others. Okay? All of those are potential nucleophilic sites, which then means you have to find an electrophile. Where do you have electrophilic sites? 1, 2, 3. I'll simplify that again. It's only 2 because identical, mirror images. Okay? So take a look at those possible options and see how they can connect up and match up. Just to be even more hint-based, the green alpha hydrogens that we can make nucleophiles will only react with which electrophile? Why will they not react with the other electrophile? It's not even that they're too small. That's actually why they were acidic. Okay? It is interacting with those. That's what makes those nucleophiles. Okay? The last one will only do its aldol condensation with the other electrophile. 3 possible products, draw all 3. One of them is awful to draw. Like you'll have a really hard time with it. Okay? The other 2 you should be able to draw reasonably well, though it may not look pretty, but you should be able to do it. Okay? You guys want to make that a quiz for Monday? No? Okay, so we won't make that a quiz for Monday. I'll try and draw up the answers so you've got answers to that. Wow, apparently copying and pasting changed all my slides. So the rest of this is now chapter 19. There's something like 30 or 40 slides here. I want to kind of jump through to the important parts. The reason this slide is on here is that when we're looking at synthesis, we need to look at how we can potentially combine 2 pieces. And when we're combining 2 pieces, we are looking for bits of information. That bits of information is charge. Identify the charge on your atoms. If we take a look at these 2 starting materials, would I expect these 2 pieces to react with each other? Why not? They're both partial positives. They're both electrophiles. No reaction can possibly occur here. How can I make a reaction occur? What would I have to do?
You can turn the oxygen negative.
Okay, there's an interesting question. How can I make the oxygen a nucleophile? It would have to take those electrons, but then I have to finish off that positive carbon. So how can I make sure that carbon is no longer positive? I need to add another nucleophile. So we could add a hydride nucleophile and say BH4, sodium borohydride, lithium aluminum hydride. Those could go through and do a reduction at that point to make that oxygen now negative. Now it could react with the other species. What else could we do?
Could you add magnesium to the one, right?
If we react the other one with magnesium, I can now make that carbon negatively charged. Now my negative can attack my positive directly. Okay? That switch right there, I was always confused by that term, and either the textbook did a good job of it or I just happened to be in the right state of mind. Converting that positive carbon to now becoming negative is known as that word with a U. Umpalung chemistry. The Wittig reagent does the same thing. We convert a carbon that is partially positive due to that halide to becoming a nucleophile, partially negative. It's known as an Umpalung chemical reaction. You are changing the charge on an atom from positive to negative or potentially negative to positive. Okay? Polarity reversal. Not that big of a deal. I don't think I'd ever ask a question on it, but it's just a weird word. All of your organic metallic reagents do this thing. We convert positive carbons into negative carbons.
That's essentially the Grignard reaction.
Your Grignard reaction does that, yes. So, and that's where this is important, is we now look at all of our reactions that form carbon-carbon bonds. Okay? And so we've got cyanides reacting with carbonyls, doing a nucleophilic addition reaction. Right? We've got your Wittig reagent with carbonyls, doing again a nucleophilic addition. Okay? And the last one, we can make enolates. The enolates can react with carbonyls in a nucleophilic addition. Notice that almost all of these are doing nucleophilic addition reactions. Okay? Your textbook also listed these last two ones, cyanides with your alpha-beta unsaturated ketones and your enolates with alpha-beta unsaturated ketones, or carbonyls. I thought this was kind of interesting because they're summarizing these. These kind of figures are in the back of your book. Use them. They are helpful. Okay? There's lots of them, so it may be difficult to sort through, but use them when working with synthesis. Okay? Just to be obnoxious, are there other carbon-carbon forming reactions? Yeah, like? Someone maybe started to say it. I'm surprised it's not up here. We just talked about it. Grignard reactions. Grignard reactions are carbon-carbon forming reactions. I don't know why your textbook decided to not include those on this sequence of slides, but those are carbon-carbon forming bonds. Your carbon-carbon bond forming reactions are very, very limited. We don't have a whole lot of them, okay? Which is why when you go through and look at those types of reactions, say the carbon-carbon one where it was carbon-magnesium, what did we do with that reaction? We named it Grignard. The other carbon-carbon one that attacks beta positions, Gilman, we named it. Wittig, we named it. Our enolates are officially Michael additions. Pretty much everything with a carbon nucleophile gets named because they're really hard to make. You're doing goofy chemistry. Okay? Carbon is the least electronegative of our nonmetals except for hydrogen, which means in almost all reactions, carbon should be acting as an electrophile, not a nucleophile. So if we can make it a nucleophile, boom, attach your name to it. Okay? This idea of selective reagents pops up when looking at synthesis. So we've got a couple reactions here. If we start with, what is this group called? OTS? Don't tell me HOTS. A tosylate. What was special about OTS? It's a great leaving group. Okay? Well, what types of reactions have leaving groups? Substitution and elimination. So depending on the conditions, I can have that compound either do an elimination or a substitution. Okay? So depending on the reagent I add, I may get different results. So I want to be careful with the reagents I add. Sodium chloride in that first case is a selective reagent. It will only do the substitution. Why will it only do the substitution? We have a good leaving group, yes, but why does chloride only do substitution and not the elimination? Getting at the right idea. Is chloride a strong base? No, it's a horrible base. It can't do the elimination because chloride is not a base. It'll only do the substitution. If I now change my conditions around where I only want to do the elimination, I should choose something that acts only as a base. That's what they're referencing when they're talking about selective reactions, that they can only do one thing. We've been doing lots of selective reactions throughout the semester. And when things came up that weren't selective, we addressed those and said, well, why is it not selective? What else can it do? Okay, so you guys are already aware of this concept. You just haven't attached a name to it. Okay? Other examples. Okay? If we were going to try to form an enolate to do an alkylation reaction, if we used LDA, we end up alkylating on the kinetic side, getting the kinetic product. If we use T-butoxide, we get the thermodynamic product. Those are selective because if I use T-butoxide, I will only get the thermodynamic product. I'll only get the thermodynamic enolate, which means I only get the thermodynamic alkylation. Okay? So Be careful with the reagents you choose. This is where identifying what you want first, like we did with that previous synthesis, the synthesis we started with. Well, I wanted a strong base. Which strong base? By first giving that information of, I need a base, you can then start to refine your answer. Don't just immediately start slapping bases out there and getting super specific, because you may pick a reagent that's not selective. Okay? If you start with the broader term and whittle your way down, you should get closer to your answer quicker. Okay? Removing functional groups. Okay? In first semester, we talked about this, and in fact, a large section of this chapter is questions or comments that we've made in first semester, so we'll whip through those pretty quickly. Okay? We've seen this reaction already. This reaction was our Wolff-Kishner reaction. What occurred? What's that? We removed the carbonyl. Yes, that's what occurred. What type of reaction? We did an addition reaction, followed by, I mean, it's kind of weird. Yeah, actually, I'd have to look at that mechanism, because all you see here is just straight up addition. I'd actually have to look at each step of that mechanism. It's not as straightforward as I would have thought. But we got another name for it that is straightforward. It's a reduction. We removed oxygen bonds and we replaced them with hydrogen. We've got a reduction. Okay? This is nice because if I look at this product, okay, what chemistry is available at any of those carbons? Very little to nothing. Okay? That's a bit tedious to try and think backwards from. But if I know I can use a carbonyl compound to, say, add a methyl group, and then remove the carbonyl compound through a reduction, I can get to my final product. Okay? So it's starting to stack reagents. We can use the carbonyl to do some carbon-carbon forming reactions, and then we can get rid of the carbonyl by doing a reduction. One of those reductions we've seen, the Wolff-Kishner reduction. And we saw that because our nitrogen acted as our nucleophile. We did a nucleophilic addition at first that then was followed by a sequence of other reactions. Okay? There's another reduction known as the Clemmensen Reduction. Okay? Again, you don't need to know the name. Be familiar with the chemicals. You're starting with a carbonyl compound and you are ending with alkane. Full-on reduction all the way down. You're adding HCl and then some weird metal mess. Okay? And by weird metal mess, I've seen zinc, I've seen mercury, I've seen tin. Okay? Tons of different metal messes can go through and do this reduction. Okay? Officially, the Clemmensen is the zinc, the zinc-mercury amalgam. But you can see tin pop up in there. I've even seen iron pop up in that. Okay? So if you're seeing a metal and acid, you're probably doing some kind of carbonyl reduction. Okay. This does some really weird chemistry, which your textbook starts to address. The hydrogens that have been added to the carbon came from where? The acid, which means those hydrogens were what charge? Positive. What charge is the carbon in our carbonyl? How do you get a positive to attack a positive? Really? This is what your metal catalyst is doing. The metal is getting oxidized. You're starting at zinc 0 and you're going to zinc 2+. Your electron source is coming from zinc, which is dumping electrons into the oxygen. Oxygen says it has too many electrons, so where does it shuttle its electrons? To the carbon, making the carbon now negative. There's our Oompa Loompa, whatever it is, picking up our acidic hydrogen. Okay? I'm glad that's not someone's name, because that would have been really offensive. Okay? Last one, Raney-Nickel Reduction. What's happening in that very first step? kind of a protecting group. It sure looks like a protecting group. It's kind of an acetal, but with sulfurs in it, we have to change it. It can't be just called an acetal anymore. We reference it as a thioacetal. What kind of chemistry did you do? In that first step, it's not a reduction, and it's not even really protection, because the next step actually gets rid of it altogether. Get rid of protection. It's not protection. It's actually doing the opposite of protection. What did the sulfur do to the oxygen? Kind of a substitution. We did a nucleophilic addition. Okay. That acetal chemistry we went through, that was in which chapter? Nucleophilic addition. Guess what the sulfur is doing? A nucleophilic addition. Okay. That's what's happening in that first step. That species, the thioacetal, reacts very strongly to this catalyst, the Raney-Nickel, in the presence of hydrogen, cleaves off the thioacetal back to our thiol, and we end up with hydrogens replacing it all together. Okay? So yet another way to remove the carbonyl. Why do we need multiple ways to remove a carbonyl? Is the chemistry different for each of these? What if there's a functional group in there that's also an electrophile? What will happen when we throw in the sulfur? The sulfur acted as a nucleophile. If I have a second functional group in there that's an electrophile, the sulfur attacks it, not the carbonyl. Okay? So we have to be careful and aware of other chemistries within our structure, because that may prevent us from doing one form of reduction over another. Okay? Your textbook has a nice slide, or a reference table in your textbook, which I'll just tell you to take a look at, that tells you what's happening within each of those reactions. Okay? So it's telling you when to avoid those reactions. We just talked about the Raney-Nickel one. If we have something that's susceptible to nucleophilic attack, like a second electrophile. Okay? So be aware of those limitations. That could potentially show up, though usually fairly rarely. Other hydrogenations. We've talked about these. Hydrogen, palladium, or platinum. Okay? This is officially where we should have been talking about it, because it's now finally shown up. Okay? These are still an addition reaction. They are catalyzed by the metal to facilitate a nucleophilic addition to them. Okay? So we can take an alkene, and I can convert it to an alkane by just adding hydrogen and platinum or palladium. You've seen that, right? You've seen the pretty picture? I like the other picture we used before better, but hey, can't have everything. Same thing. We could also do this to alkynes, okay? Because all it is a pi bond. So we could now add hydrogen and, say, platinum or palladium to an alkyne, okay? And it will reduce one of those pi bonds. Except what happens if I have an alkene and hydrogen and a metal catalyst? It reduces it again. So we run into a selectivity issue. Our reducing agent won't stop at the alkene. It'll continue on to the alkane. Well, that kind of sucks. Okay? So what we might want to do is say, are there other reagents that can get me to stop at an alkene? Okay? So it's thinking about different chemicals and different ways to do it. One way to do that is to use something known as a poisoned catalyst. So instead of just adding in straight metal, we add in a metal that has a bunch of junk on it. That junk prevents your substrate from interacting appropriately, and it then stalls the reaction. So the common one is something known as Lindlar's catalyst. You use a metal carbonate or a metal sulfate as your poison, and quinoline. Those compounds block active sites within the metal. They prevent the second reduction, which means we end with the alkene. A feature of that reaction, which we feature or disfeature, depending on your perspective, is that the hydrogens are always added syn, because the pi bond sticks to the metal. Then the hydrogens come in from the side. They are added to the same side of the pi bond. Okay, so you will always end up with a cis alkene when you use these types of reducing agents. Okay? So Lindlar's, if it's poisoned, Lindlar's will do it. The other one that you may see is reference to palladium or platinum with some other kind of toxic stuff in it. Okay? So they may actually write it out instead of the name of the catalyst, they'll give you the actual chemical formula. Okay? Just be aware that there's multiple ways to look at the same thing. What if you wanted a trans product? Anybody remember that one? We don't use hydrogen as our source. We use sodium solid and ammonia. Okay. It's a dissolving metal reduction. It's a radical reaction. Sucks but that's what it does. And you end up with a trans alkene. Okay. We will look at that mechanism again later in the semester when we talk about aromatic rings, because we can use that to reduce aromatic rings. Okay. So, variety of ways that you can go through and reduce things. They've given you a whole list of different reducing conditions. All of those are adding hydrogen. The only thing that's changing is we are changing the reaction conditions, temperature and pressure, which then changes which functional group you're reducing. More importantly to notice, if you look at that, in fact, the nitrile one, what else do you see within that beyond the nitrile? The polar pi bond, okay, a second polar pi bond that was not reduced. Okay. So those conditions will reduce the nitrile, but not the other polar pi bond in that compound, the ester. Okay. So we can tweak those conditions in certain circumstances to favor the reduction of only one reagent over another. Okay. That gets way too far into the details of what's happening within those reductions. I do not expect you to know that if you want to reduce a nitrile, you need hydrogen, Raney-Nickel, 80 degrees and 75 atmospheres. What I expect you to know is that hydrogen and a metal catalyst will reduce it. Okay? I'm going to skip the synthesis. We're going to skip protecting groups. And we will come back to that after the exam. But this last section I want to talk about really quickly. Oxidation. We can take an alcohol and we can oxidize that to the carbonyl compound. Okay. To go through and do the oxidation, you need an oxidizable hydrogen. So if we look at the primary alcohol, there are two hydrogens at that carbon. I can remove one and I'd end up with aldehyde. I can remove a second and I'd end up with a carboxylic acid. If I have a secondary alcohol, how many oxidizable hydrogens are at that carbon? Only one, which means what happens after I remove that first hydrogen? I'm stuck. I can't oxidize anymore. There's no more hydrogens to remove. I don't do a second oxidation. In the case of a tertiary alcohol, there's no hydrogens whatsoever. I can't oxidize that at all. Okay, so it's recognizing which alcohol you have. How can you potentially oxidize that down? As far as the reagents go, there are only two reagents that you need to know as far as oxidizing alcohols. Both of them, believe it or not, are chromic acid. Chromic acid begins with, just like cookies, C, thank you. Okay. The other chromic acid reagent is politically correct chromic acid, or PCC. Chromic acid, stupid strong oxidizer. So what happens when you add an alcohol to chromic acid? You go to the extreme right on this chart. You push it all the way oxidized. That's what chromic acid does. It cannot stop, like the Cookie Monster. Politically correct chromic acid is the milder version, okay, of the Cookie Monster. and we now have Elmo. Elmo can oxidize once, but he can't oxidize again. So he can take the alcohol to the ketone in the case of a secondary alcohol, but he cannot oxidize anymore. Why can he not oxidize anymore? There's no more hydrogen. So it's the same result. Elmo attacks our primary alcohol. What happens? Goes to the aldehyde. He's stuck. He cannot oxidize anymore because he is politically correct. What happens if you're given an aldehyde? Still can't oxidize. Okay? It will oxidize the alcohol down to the carbonyl. It will not do it a second time. Okay? I will have to stop there because I've way exceeded my time. I apologize for that. You will not see questions on... Let's scan through this real quickly. Please do feel free to pack up. Your protecting groups on alcohols you won't see. Protecting groups on carbonyls, fair game. That's our acetals, which is that one. Yep. So no protecting groups on alcohols to worry about. You do not need to worry about the Y necessarily with chromic acid versus PCC. At this point, all I expect you to be able to do is say PCC stops at the aldehyde or the ketone. Chromic acid bulldozes through as far as it can. So it'll go to the carboxylic acid or the ketone. The Y we will talk about right after the exam. Or wait, why am I saying exam? We got another day.
After the review. We are reviewing after the We typically review.
I have an exam tomorrow, so that's why I'm thinking about it. So we will finish the oxidizing explanations on Monday. We will not do the protecting group of alcohols. I may talk about them just to say we've done it, but it's not going to show up on the exam. It's not important enough that I really care about it. Okay? Good thing I recorded that. But we will talk about the rest of the oxidations. Dang it, why did I speed all the way through that? Freaking damn it. So Monday, finish off oxidations, and we'll go back through the stuff that I went through too fast, so you can go back and say, hey, hold up, you talked too fast. Okay? Sorry.